what exactly does linear function approximation do? Right. So, ideally what you would want it to do is the following, right. So, I have some abstract space in which I have some v pi that is being represented, right. So, I have an abstract space in which v pi is represented, and there is some plane, right. There is some space which kind of is spanned by my feature vectors phi, right. There is some space that is spanned by my feature vectors phi, right, but there is my real value function v pi sitting in some other space. This is clear, right. So, what space would v pi reside in? Suppose I have n states, right. So, v pi resides in a r power n state space, right. So, it resides in r power n state space, where each coordinate corresponds to the value of the respective state, right. So, the first coordinate will be the value of the first state, the second coordinate will be the value of the second state, and so on and so forth. It will be a point in Rn, right, and my phi might be something that spans a much smaller state space, right. My phi could be something like r power k, where ideally I would like that to be the case, because I do not want to be representing an n dimensional state, in which case I can represent the tabular form, right. I can represent the actual value function, right. So, I do not want this. So, k should be far less than n. So, in this case I am assuming that n is 3 and k is 2, okay, just so that I can draw. Any other higher dimensions, it will be hard for me to draw, right. So, ideally what would you want to happen, right. Let us say that right. So, that is ideally, that is what I would want my v hat pi to be, right. That is the closest possible I can get to, given that I have to stay in this plane, right. So, people must have done some kind of linear regression, curve fitting and things like that, projections, right. So, essentially what you are doing is the closest projection to the plane, right. So, this is essentially what we are trying to look for, right, and what exactly is this in terms of regression fits that you are getting? It is the least squared solution to the fit, right. So, the least square solution to the regression problem that you have, where your targets are drawn from v pi, right, will essentially be the v hat pi, right. It turns out that there are some results that show that if you are actually going to be updating v hat pi incrementally, right. So, essentially I have this vector theta which I will be updating incrementally under certain conditions on phi and so on and so forth, right. Your v hat will not converge to this. So, we will call this v hat star, right. So, I am not going to go into the proof of that thing. If you are interested, I can give you pointers. Good. When I talk about pointers, Varun just walked in. You can put the Sitsiklis and Van Roy paper on the convergence of TD with value function approximation, right. Maybe we can give a link to that paper on. I think I used to link that paper anyway from the previous editions, but since the previous editions seem to have disappeared, you can add the link to the paper, right. So, v hat star would be the least squares projection, but it turns out you will not get it normally. So, what you will end up doing, what you can end up showing is you will converge to some v hat, right, which is within a certain distance of v hat star, right. So, that distance to which you converge is bounded, right. So, it is there is within a bounded distance of v hat star you will converge, okay. So, this is basically what you can show. So, so let us not call that star, I am going to call that v hat optimal, right. That is the actual optimal thing I want, and star is the one that I will get at convergence, right. So, my v hat star will be very close to v hat optimal, but except in some rare cases it will not be v hat optimal, okay. So, why you think this is happening? Right. Ideally the best solution, because anyway you remember we are minimizing the least squares error, right, we are minimizing least squares, right, that is the way we wrote the error function, right. So ideally the minimizer should be v hat opt, right. So why are we not converging to v hat opt? Sample error, noise, what kind of noise? Non-stationarity, so that is the problem, right. Not just when you say sample error, it is essentially the target keeps changing over time, right. I pointed this out last class also, right. The target that you are updating towards keeps changing over time because you are using the v hat itself as your target, that keeps changing over time. So that introduces a little complication in the dynamics. So you cannot guarantee that you will converge to v hat opt, right. If you knew the true v pi values, right, if you knew the true v pi values, you will converge to v hat opt. If you, since you do not know the true v pi values and you are essentially bootstrapping, you end up converging to something v hat star. Okay. The nice thing is at least that given some mild conditions on phi, the distance between v hat opt and v hat star is bounded. Okay, so that is a nice thing, that's what makes what mild conditions? They have to be orthogonal, the phis have to be orthogonal, and then you have linear, no, not necessarily orthogonal, linear independence is fine, they have to be linearly independent and you have to sample on policy, right. So on policy sampling is very important. If your linear function approximation with dynamic programming style updates can be shown to diverge. So dynamic programming does uniform sweeps, right, it is not on policy, every state is updated equally often, right. So that is certainly not on policy, and you can show that that will actually diverge, right. So think of what is possibly happening in the update setup, right. So I start off with some, suppose I want to do an updation on my, let's say even on this case, right, I have a fixed pi, right. So what do I start off with? I start off with some guess for v, say I will start off with some v naught, right. So I start off with some representation for v naught, right. So that will be somewhere in this space. Then what do I do? I do some kind of an update operation, right. So this is, I am just using my Bellman operator to summarize it, but if it is Q learning or if it is TD learning, for everything I can write a corresponding operator, right. So the TD learning operator would essentially be some kind of a sampled version of this Bellman operator, right. So essentially I apply some kind of an approximation of the Bellman operator to my V, and what will I do? I will get a V1, right, but my V1 will typically be not here, right. So I start off with some V naught, right, there is no approximation here, right. I start off with a V naught, I apply T pi on it, right, whether it is a one round of TD update, right, or anything else, I apply something on it, right. Then what will essentially happen is this will go to V1, V1, right. So V naught, when I apply pi on it, T pi on it, will go to V1, right, and what do I do at that point? I project it back, because that is all I can represent, right. So that is the best I can do. In some sense what I am essentially doing is projecting it back till it hits this space, so that is my V1 hat, right. Right. So I apply a see, normally the projection matrix projection operator is indicated by P or rho, right. So I am using P here, even though P we are using for transition probability, I am also using P for the projection, right. So I am do a projection. So in some sense that is a joint operation I use to go from V naught hat to V1 hat, right. So in this case there is no approximation really, because I started there, but I can do this. So this takes me to V1 hat, right, and I keep doing this again and again until I converge to.
How is it joint? Because you have to serially do it, right?
Do I do it that way? If you think of the update that I am doing, but I just change the thetas directly, right?
Correct.
Yeah, the way I change the thetas is I find the gradient of the performance in the direction, then change the theta in the opposite direction of the gradient, right? So that's essentially what I do. I just do gradient descent. I look at the approximation error, right, and I go in the opposite direction. So where did I compute the new V1? I'm not explicitly computing V1, right? I basically computed V1 hat anyway.
I agree, but
Conceptually, what we are doing is this kind of a, well, you can think of it as a composition, right? I apply T followed by P. I mean, if the word joint is confusing you, okay, it's a composition operator. Okay, great. So this is essentially what is happening in terms of what we are trying to do in function approximation, right? So one thing which people started thinking about is, hey, we are trying to solve a regression problem, right? Can we set it up as a proper regression problem? And so what do I mean by set it up as a proper regression problem? How do you normally solve linear regression problems? You are given some data set, right? You are given some x1 to xk as your input dimensions, and then you are given some y, right? So like that you are given many such data vectors, and then you form a matrix out of it. You form a, what is the matrix called? What is the matrix called? Huh? Data matrix. Yeah, you should know a different name for it. You have sat through enough of Nandan's classes.
Hut matrix.
Huh?
Hut matrix.
Oh, no, hat matrix.
No, that's different.
That's exact. You will get after y hat.
I forgot.
No one else from DOMs here, no one, right?
I forgot.
You are the only DOMs representative. I am going to pick on you.
I forgot.
Sometimes called the design matrix. Right, so the data that you get is also called the design. I am pretty sure many of you have heard the term design matrix. It essentially means that data set, X, all the X's, right? So the capital X that you write by combining all the X's for the design. So normal regression problem will require us to have something like so I'll have an input vector and a y, and then I'll have this indexed over, right? If I want to do something like this for value function approximation, what should I do? I should have some vector S, right? So basically we have right. So this is what I should have, right? This should be the data that I should feed to the regressor. Like this, I should have some n samples. It makes sense, right? My only problem here is my V of s. I don't know my V of s. So what we do for V of s? Here I am going to assume that my V of s comes from right, some phi transpose S into theta, right. You could, if you want solving this in Monte Carlo way. If you want to do TD, then you can set it up as a Monte Carlo problem, and then you could just take the return starting from that state and then give that as the sample of the V pi. You could set up a function. That's a perfectly valid way of doing things, but uninteresting. Right? Why is it uninteresting? Because what you will converge to, we talked about this, right? Even I had this question in the exam also, right? So what will you converge to if you use Monte Carlo, a fixed sample Monte Carlo? It's the least squares minimizer of the prediction of the return, right? But what you will converge to if you use TD for a fixed sample is the certainty equivalence estimate, say the Markov model. That's a more interesting quantity to estimate than just the least squares estimator, right? Least squares predictor. So anyway, right? So we can assume that Vs is given by this, right? And for my current setting of theta, right, I could just plug this in here, right? So whatever is I make an initial guess for theta, then I make one big data set like this. Then what I do, I choose my favorite least square solver, right, and get a new estimate for theta, right. So then I keep doing this again and again, right. So now if you think about it, my input is in the form of some phi's, right, and the output is in the form of some phi times theta, right. Now I can actually try to solve this in some kind of a sorry?
Will we be using all the data points?
What are all the data points here? We are talking about all the states. We will come to the data generation part a little bit, right, later. Almost surely you will probably not have samples for all the states, right, but then for some states you might have more samples, right. So great. So now let's look at it. Okay. So what I really want is, suppose I have this whole operation that is happening, right? My p times p pi of v, okay, of v pi hat equal to v pi hat, right? This is my fixed point. Right? This is essentially what I want to achieve, right? I want to get to my fixed point solution. So if I get to my fixed point, what will I have? So what will this look like? Right? Now I fix my pi, right. So this will become my p pi, if you remember the matrix p pi that we had earlier. So that is essentially the transition reduced to what happens when I take my action corresponding to the state. So instead of p s a s prime, right, it will be p s pi of s s prime, right. So that is this matrix. So I have reduced it, right. I can remove the action column from there. So this is essentially p s s prime, right, where the action is fixed to be pi of s. We looked at this matrix when we saw the convergence in the of the Bellman operator, right. Now what is remaining? I really have to look at the projection business, right. So I have written the t pi operator here, and now I have to look at what the projection is going to look like. What will the projection look like? What is x? What is x here? Right, that is a projection, right. If you remember the linear regression solution, okay, where phi is written for all the states, right. Phi of s is one row corresponding to state. When I do not write any arguments to phi, it is the entire matrix. So each row corresponds to one state, right. So I have written the entire Bellman equation there for you. Right. So it turns out that with a slight change, because I will use it later, I will just write it down here, I will use it later. I can also write this for where this one will be taken appropriately for S prime, right. So whatever is pi of S prime, so q pi of S prime comma pi S prime, okay, that will be the q pi here, and the one other change is phi will be phi of SA, right. Phi will be defined on state action pairs, right. Remember we talked about how would you go from V pi to Q pi. I gave you several methods, right. One of them was to have phi SA, right, instead of phi S, right. I am assuming people remember anything we did in the last class, right. I am sorry, I am assuming people remember everything we did in the last class, right. And so that is the change here, right. So phi will be phi SA, right, and this is different, and this you will have to be careful about, okay. So otherwise you can write something very similar to what we did for V, okay. So now what do we do, now that we have this, so I can write this as that is the entire vector, okay. So this is the phi matrix, right, phi theta. So each row will get multiplied by theta, so that will give me the whole vector V, right. This is V pi, so I do not know what to call it, so theta pi. Yeah. So perils of on the fly notation translation. So whenever I put some symbol there which you have not seen before, please stop and ask me. It might be something which I forgot to translate. Anyway, right. So I have replaced my V hat with my phi theta pi. Where? Here? No. So this is phi transpose, yes, because I am doing one, this is a vector thing.
So those are not
huh? This is a matrix phi, right. So when I take, this will essentially give me a vector. So this is phi theta. Okay, this is matrix multiplication, not inner product of two vectors. Okay, make sense? So where the phi, each row in the phi is a state, right. When I take this, my theta is going to go like this, it will multiply the whole state and it will give me the value for that state, okay. Fine. Right, now do you want me to do the algebra, or you guys want to do it and then tell me what theta pi would be? I can take it to that side, do some simplification, blah blah blah. Okay, so people are convinced. Okay, good. So now I am going to do a little bit of the thing. So one of the, so this gives you the least square solution, yeah.
So shouldn't R be also R pi?
Sorry?
R
Huh?
shouldn't it be R pi?
R should be R pi. Yes. Everywhere, I mean. So this is the least square solution, right? So what is striking about this least square solution is that it treats everything as an equal contributor towards the error, right? Every state as an equal contributor towards the error, right? Every sample as an equal contributor towards the error. But then we know that that is not always the right thing to do. Why? Well, we have a small enough expression power, right? So we really want to approximate those states that are more important for us, right, and then leave out those states that are not that important, right. So what you do essentially is, instead of looking at minimizing a least squares fit, you minimize a weighted least squares fit. So then what would happen is, in your solution you will have a weight cropping up at different points, right. So what we will do is, we will rewrite this, and while I do the rewriting I will also introduce the weight, right. I am not going to redo the whole thing again. So I am going to write a weighted version. Phi transpose So where W is some kind of a weight function over all states, right, that tells you how much you want to weigh a state by. What is the typical weight function that you want to use? The steady state probability distribution, right, steady state probability distribution. It could be anything else, right? Whatever takes your fancy, right. So you could use that weighted probability distribution. So this is essentially what we get. So I am going to make it a little simple. I am going to call that A, I am going to call this B. So I end up getting A into B. So the rewriting is not just for fancy, okay. So this is going to allow us to do look at each one of those quantities there a little closely and see what they are actually doing. So A and B, okay. Yes, but now we are not doing any incremental updates or anything, right? I am giving you a bunch of samples and I am solving for it. Yeah. So I wanted to approximate the steady state distribution, right? And if I do the sampling on policy, I will approximate it. That's what I was basically doing.
So we were saying that it should be only that, but here you mentioned that it can be resolved.
Yeah. So that's a good point. So all I am talking about now is getting the least squares fit for a given set of samples, right. Given a fixed set of samples, I am trying to get a least squares fit, right, and I can get that least squares fit regardless of what the W is, right. I will get a least squares fit given a set of samples, right. I have no guarantee about how good that fit will be from the viewpoint of my true V hat opt, right. If I use any arbitrary thing, it's in terms of how close I am to V hat opt, I have no guarantees if I use any arbitrary W, right. So we know that if it is on policy, right, then we will get that V hat star given infinite number of samples, right. I mean, of course, so as it's all asymptotic convergence guarantees, right. The more samples you are given, the closer you will be to V hat star, right, but you will never get to V hat opt, right, and that is guaranteed if your W is going to be your on policy distribution, right. But if I am looking at any fixed set of samples and I am talking about just getting some estimate that fits that sample, I can choose whatever W I want, right. I said you would want it to be the steady state distribution, but even if you choose something else it is fine. Why would you want to choose something else? Huh? Could it be because you do not know the steady state distribution? Right, you do not know the steady state distribution. One way of approximating it is just to look at the relative frequencies in the samples that you have drawn already, right. That could be very far away from the steady state distribution. Right. In fact, we end up using that distribution only because you do not know what the steady state distribution is. So, you end up using the distribution that you infer from the samples that you have drawn. Right. Are people with me or people lost? No? Okay. See, I said that, I mean, if W should be the steady state distribution probabilities, right, all of you agreed to that, right? That is the ideal situation that we want, right, but we do not know what the steady state distribution is. I mean, you would not know that until you either you solve the Markov chain set up by the policy and then you know what it is, but for solving that you need the transition probabilities, so that is not going to happen. So, you do not know what the true steady state distributions are, right. How do you approximate those steady state distributions? By counting it from the sample that you have, right. Right, when you count from any fixed set of samples, right, the distribution that you infer can be something very far away from the true W that you want, right. The weights that you get by inferring from a fixed set of data could be very far from the W that you want. So, if the data is very large, right, as t tends to infinity, doing an incremental update will approximate the W's. But we are not talking about t tending to infinity, we are talking about a fixed set of samples here. So, given a fixed set of samples, the W that you get can be very far away from the true W. So, you just live with it, okay. So, let us go look, write out A. Right. So, this is essentially my P pi. Right, that transpose comes from this whole thing gets modified because I went from a matrix notation to a individual entry notation, right. So, essentially if you look at what is the products that are being computed here, this will work out correctly, okay. So, I have flipped the, if you do not think I have flipped the transpose, that is because I went from the matrix to component wise notation. Right. So, this phi s times phi s is the product that you have here, right, and it will sum over all s prime, so this will drop out. Okay, so essentially you are getting your phi s product from here, right. Essentially I have added an additional unnecessary p s a s prime to that product, okay, so that I can take it inside the summation. Okay, does it make sense? Right, so I have for this term I have added an unnecessary p s prime term to it, so that I can take it inside the inner summation, right. So that is essentially what I have done. The rest of it is the same, right, nothing else, no fancy tricks here, right. The reason we did this is so that we can write this as some kind of a sampled thing, this kind of an expectation. So if you think about it, what I say, this is some kind of a weighted sum of this quantity. Right. So what I can do now, I can keep sampling transitions from s to s prime according to this distribution, right, compute this quantity, the difference between s and s prime, right, I compute this quantity again and again by sampling according to this distribution, right, and then take a average weighted by how much importance I want to give to each of the states, and that gives me my A, right. So we got around one of the biggest problems. Nobody actually asked me how can I say I have solved the linear regression problem here when I actually have the p pi in here, right. I have the p pi in here and I have the r in here, right. I can't say that I have solved the linear regression problem from samples, right, because I am assuming that I know the model, and if I know the model I might as well solve the model directly, right. Why am I doing this? The whole idea of doing all of this is I do not know the model, right. So I need to somehow have figured out what my p pi is and r pi is instead of figuring out p and r directly, right. So we can have actually a way of estimating the A matrix directly, right. So what I can say is, given a set of samples, right, of the form, my samples are going to be of the form I am going to get L such samples of this form. Okay. Remember, so this is the current state, action, reward, and the next state. Okay, that's the form of samples I am going to get. Okay. So in our normal notation, it will be ST, AT, RT plus 1, ST plus 1. Right. The I index just denotes is the ith sample. Okay, nothing to do with the time indexing. Right, does it make sense? Right, this I is nothing to do with our time index, it just denotes its ith sample. Okay. So I am going to get states like this. Now what I can do is I can form an estimate for A tilde this is my A tilde. Okay, so A is fine. What about B? Sorry?
The third step, P transpose. Here.
I'm not 100% sure.
Is it just a number?
Yeah, P is just a number, right? So the vector is the phi, right? So it's fine, right? So what about B? Can you do B also something like this? We can, right? It's almost clear. Was it? Good question. Yeah. So where did the W go?
That just comes from the number of times it appears in the data.
Yeah. So this will get. So I'm kind of wrapping the W and the P into the frequency. Right. So yeah, we are making a very strong assumption that everything is fine, right? So that the number of times S occurs here, right, is exactly the number of times you want according to the W, right? Then it's fine. Okay. So I can do something. Okay, let me do B first before I move on to anything else. Right. So that is what R pi is. People remember the R pi thing, right? So R pi is essentially summation over all S prime, P S pi S S prime into R S pi S S prime. So which is essentially the expected reward that you are going to get. I mean, we wrote it as an expectation. I am just writing it as a simple thing here. Okay. And I can do the same trick that I did last time. I took the phi inside. Right. So just like last time, I have taken the phi inside. So what I can do now is the same thing that we did earlier for A. So I can write B tilde as sorry. Right, I can do that. So I can also write the action version of this, right? So yeah.
There is a transpose.
Hmm?
There is a transpose in the third bracket.
Here. There is no transpose one. No, so like I was saying, right, the phi transpose here, you lose the transpose when I write it component wise. So I can write the action version of it also like this, right? You remember we wrote the same thing earlier here. So I can run through this, simplify the whole thing, right? And I can get the same thing here, right? Except I am leaving out this part. I want you to fill it in. Tell me what should go there. Huh?
No, pi of this side.
pi is more.
Okay. So this is the tricky part. So I might not have this in my data. In SI prime, I might not have done CSI prime. So we have to be careful about whenever we use these things, right? So you make sure that you have done pi s. That's the on policy part of it, right? And likewise, I can do the B tilde here. This is relatively straightforward. In fact, that's what I wrote first. So this kind of an approach where we use an estimated A tilde and a B tilde, right, and solve for a value function pi is called LSTD, least squares TD, right. So when you operate with the V function, it is LSTD. When you operate with the Q function, it is oh, it's called LSTDQ. Okay. So you have LSTD and LSTDQ, and you also have an LSTD lambda, where you do this for TD lambda as well. Okay. There things become a little tricky. So here, in some sense, my A is a repository of my model, right. So in the LSTD lambda, the gamma lambda terms will appear here also. Here the gamma term appears, right. When you do LSTD lambda, you will get a gamma lambda term in your A matrix, right. So that is the trickier part, right. So that is essentially what will happen in difference between LSTD and LSTD lambda. It is very convenient because it looks like it is a very small change, in fact, right. And is there something else that you note here? So when writing my solution for theta, I am solving for theta, right, and in case you forgot, with all this mechanizations we are doing, we are actually solving for theta pi, right. So when you are solving for theta pi, I have A this side, I have B that side, right. I am going to do now A tilde, B tilde, and what is one thing that you notice if I have to do A tilde, B tilde? Huh? It should be invertible. Let us assume that if fees are if my fees are linearly independent, it will be invertible, right. I can show the little linear algebra. I can show that if the fees are linearly independent, okay, this will be this will be invertible, and then what else? My 1 by L will go away, right. So the 1 by L, I do not have to carry it around. I can just throw it away because it will get cancelled out on the A and the B, right. My 1 by L will go away, and then what are you left with? Just a summation of terms of this side, right. So what does this tell you? That as I keep getting more transitions, I can just keep adding to the A matrix, right. It is very easy to update my A matrix incrementally, right. I can just keep doing these iterations, right, and then as I am sampling more states, I just keep adding to the A matrix. So I can get a much larger, I can keep improving my estimate of the value function, right, as I keep getting more transitions. So at any point of time, I can just take my current state of the A matrix and solve it for V pi or Q pi. Okay, great. So this is called LSTD or LSTDQ.